Just want to check, did anybody not get an email from me today morning? Everybody got?
I think I did.
Oh, you did? Okay, so maybe we can add him to the list, because so those who are registered for the course kind of copied all the email addresses, and so just sent you a link to the website, and for your information now, a few things. There's a calendar which we'll keep updating as the course moves along. There's a set of slides that were initially prepared by Professor Farhan Rana, who used to teach this course a long time ago. It's a pretty long set of slides. It covers everything we're going to kind of talk about in the course and a bit more. But it's a really good resource to keep reading through as we move through the lectures. And also the handout, first handout, which is more of a commentary of the lectures, what I'm talking about in the lectures, with some, sometimes a little more or additions of that are also posted here as handout 1. Okay? And that also will be updated as we move through the course. So at this stage, so I would say that these handouts and the set of slides that are uploaded are kind of the required reading. So you kind of do side by side. Okay, so. I think Professor Rana's notes, slides are also written out in great detail, so you can refer to them as well. Okay. The next thing, the last thing is that the first assignment would be posted probably tomorrow, and so you will get an email about that. Reith wanted to also discuss that we are setting up this. He has set up the Piazza site for discussions, for assignment discussions, and so you will need to register for it, right?
Yeah,
is that right, Reith?
Today evening, so there's a link you can register, like say homework discussions, general discussions you can have on that. And in future we'll send out announcements through the Piazza, so you'll receive an email as well. But yeah,
Okay.
like all of you should go ahead and register.
Okay, all right. Any questions? Yep.
The homework assignment that's going to be posted, is that on material we've already covered, or is it going to be on material that we will also be covering in the next few lectures?
So it will, the problems there would be such that they will all be covered, well in advance of the due date. So, yeah, I mean, so it may be that some of the things that we'll talk about next Monday might show up in the assignment posted this Friday, but the assignment would be due later. So, yeah. Okay, so and just to kind of so the handouts are here, and I'm basically kind of writing down what I talked to you in the lecture. So it's kind of, you'll see it's pretty much similar what we talked about in the lectures, but then so there's some more details, and then the set of slides. I think. Wait, what happened here? I didn't mean to do that, but so the set of slides is you can follow through it. I'll be following it roughly, so you can all the details of the formulas, everything would be from the slides too, so you can have a look. Okay, so and you can see we have been talking about these things in the class right now, right? So and just to also be clear, we spend the last class talking about why do we need quantum to understand electrons in semiconductors or metals and other materials, so for example, in this set of slides, the quantum mechanics is basically kind of comes at you without the reasoning that went into it, why. So that it comes here because it's assumed that you know that you have had a course. So, but if you want to get the background and a little more, so that's in the handouts. And also, if you have taken a course on quantum, I would really suggest going back and brushing up a little bit. Okay. Okay. So let's continue from where we were in the last class, and we'll screen down. Okay. So towards the end of the class last on Tuesday, we were discussing roughly the fact that the electrons, initially people realized photons were quantized, they carried energies in discrete packets, and then people, de Broglie and Davison-Germer experiment, they showed that even electrons, which have mass, are also following wave-like behavior. I mean, they're subject to similar. They showed up experimentally in a very similar way as photons did or light did, right? So the question that we are really trying to answer is what we are really after is what is the laws of motion? What is the mechanics? How do I control the mechanics of electrons in a solid or wherever, in air, in vacuum, in metal? And so we are really searching for a corresponding Newton's law, right? But for electrons which have this wave-like behavior. That's what we are after, really. And that is really the Schrodinger equation, and then we're going to kind of get there today. And why are we after this? Because we have realized that there are some problems if we do not consider the wave-like nature of electrons. For example, we talked about the heat capacity of electrons, and that was predicted by classical theories. Again, I'm going to go through this a little bit. Is the if total internal energy, this is the volume of any number of particles, this is the temperature. So the heat capacity is the rays. If you give it extra energy, how much how much energy can it kind of take in and increase its temperature, right? So that's the physical meaning. And in classical physics, your internal energy is 3/2 kT, Boltzmann constant times temperature per particle. And if you have n number of particles, that's your total internal energy, right? And then we took this and you can take the n out, take your temperature derivative, and you end up with 3/2 times the density, n over v, times the Boltzmann constant, right? And this is what the classical relation says, that if I have 10 to the power 23 per centimeter cube electrons, I should have this much CV, heat capacity, and experimentally it was not verifiable. It was experimentally the values are way smaller, way smaller, right? And the values experimentally looked more like, if we are on time, we may be able to get there today, but it looked something like this, where this is the Fermi energy, and only a certain fraction of electrons seem to be contributing to the heat capacity. And this EF, we are going to, by the end of class today, we should be able to understand what this exactly means. So this is called the Fermi energy, and the Fermi energy will be written as a momentum square by the mass of the electron. We are going to show it today. This is the Fermi energy, where PF is the Fermi momentum. These all of them have the name of Fermi in it. So that's the Fermi momentum. And we can kind of see the trail of how is it related? How do you find the Fermi energy of a bunch of electrons? So that would be and we're going to do this today, okay? And the Fermi momentum is actually given very much by the de Broglie relation. Momentum is h bar times k, where k, again, is a certain characteristic number for electrons here. Is the Fermi wave vector, so. I don't think people are very creative in naming these things at that time, but and what is the Fermi wave vector? What we'll see now is, so that's momentum, energy. This will be related to the number of electrons or the density of electrons here, right? And we'll show today that this is going to be given by, for example, in three-dimensional electrons, metals, it will be given by n 1/3. So we'll see that today, where n is the electron density, volume density of electron. Volume density is in per centimeter cube, 1 over length cube, and cube root will give you 1 over length. Wave vector is 2 pi by the wavelength, right? So it must be 1 over length. Take that, multiply Planck's constant. You're completely in quantum territory right now. Momentum and momentum goes in, gives you energy, and that's what goes in here. Right? So there's additional dependence on electrons, on the electron density. And classical mechanics really cannot explain this, the reason why electrons should have so much energy. We're going to compare it today. This is a very, very high energy. And this energy, this Fermi energy, is really the root of this. The origin of this is the Pauli exclusion principle for fermions. That's why you have this. If you didn't have if you turn off Pauli exclusion principle, this will go to 0. And physically, what we're going to see is if I have all these energies allowed for electrons, and I have a lot of electrons, say big N, and I kind of try to populate, these are all the allowed energies for electrons. In classical mechanics, all the electrons can bunch out here, and they don't need to have any extra energy. But because of quantum mechanics, electrons will basically you can fill only 2 electrons in one state, actually up spin, down spin. And if you consider the spins to be separate, there's just 1 electron per state. So in that sense, we can see that why, if you fill up here, you can't fit one more. You have to go to the next, go to the next. So if I had, in classical mechanics, I would kind of fill like this. In quantum, you must go like that. There's no other way, because you're excluded from here, right? And the height here is what the maximum value we'll get is physically the Fermi energy that we're talking about. So this is purely because of this behavior of exclusion principle. Yeah.
What K is that in the KT over EF? Is that?
Yeah, sorry, I should be. It's Boltzmann constant.
Okay, that's Boltzmann.
Boltzmann constant.
Is that a K and 3 pi
Yeah.
squared?
Right. So this is the wave vector. So this small k. So whenever I write k sub b, that's the Boltzmann constant. Right? K sub. If I don't write k sub b, I would mean it's 2 pi over the wavelength of an electron, the wave vector.
Okay.
And we'll see that as the wave vector changes, if I write kf, that is a very particular wavelength. It's not a variable. So that's the Fermi wave vector.
What's the third thing in 3 pi squared times?
Okay. It's not clearly written. So that's 3 pi squared times electron density n, which is here. Same thing. Yeah. Right, so we're going to see those things too. Yeah. Okay, so kind of going back to where we were, we were discussing. We talked about the kind of historically the electron when it was diffracting off a crystal. You could see essentially you could see diffraction patterns when the electron was bouncing off a crystal, and that was clearly an indication that electron, in spite of being a particle with mass, has a wavelength associated with it. And the electrons also followed the wavelength is Planck's constant by the momentum p, so now what we're going to do is so this is the de Broglie relation, which is valid both for photons and for electrons. And we are going to kind of go and try to construct the Schrodinger equation and where does it come from? Because once it's clear why must electrons follow the Schrodinger equation, we can apply it with probably a bit more confidence and understanding. So now what we discuss is if I look at the electron, let's say in a one-dimensional picture, and because it has a wavelength, the best I can kind of do is not the electron being a point particle should be in classical physics. I should be able to say here is the electron at x is equal to 10 meters or whatever, right? But in quantum, because it's a wave, the best we can kind of do is only assign to it a wave packet. So instead of being a very precise location, and that leads to this uncertainty in the location of the electron. So it's where exactly is it? It's uncertainty associated with it. And in order to create the wave packet in k space, which is now just to be clear what I mean by k, I'm writing the momentum of the electron as Planck's constant times k, and this is the 2 pi by the wavelength of the electron. So if I had only one, if the electron had only one wavelength, it was what you call as monochromatic, from borrowing from light. If it had only one wavelength, then you couldn't create the wave packet. It will essentially kind of go, with the same amplitude forever. Right? So that's one wavelength. But the way you create a wave packet is you take, one wavelength with a very large amplitude. So I can maybe, get this amplitude, and take another wavelength with slightly different amplitude. Right? Another wavelength with even different amplitudes, and you choose the amplitudes, say, A1, A2, A3, and so on, and you have to weight them accordingly such that you can create the wave packet. That's the Fourier series, right? You can decompose any given function, any given shape, into a series of sinusoids. Right? That's what Fourier theorem says. Right? And as a result, to create a wave packet, sorry, this is still x. I'm drawing the amplitude of the wave, right? And if I now go to the k space, which is 2 pi by wavelength, what I'm trying to show here is, if you look at this, it has kind of a central frequency, or central, wavelength. Frequency in space is the wavelength, right? So it has a central frequency, and for that you will get a very large peak. You can see most of the weight is in that, right? And then you can see that if I let it spread out very wide, then I'll get even longer weight. And then by adding various wavelengths, here's another wavelength, it's 2 pi by lambda 1, 2 pi by lambda 2. A little weight here, maybe a little weight here, and so on. So this is essentially what we're saying is in k space also it's spread out now, because I've created. So yeah, there's a question.
So my question was, when we're integrating different wavelengths, we're differentiating different wavelengths as well as amplitudes?
Yes, so every wavelength, so I'll try to write that function now, right? So this will be written as a sum of a sub k, okay, times, I could write it as sine or cosine, but I'm going to write it as I kx. Okay? So for now I'm good, and I'm going to justify why. Okay? So this is basically what we're really trying to say is any function you give me in x, I can write it like that, and that's Fourier's theorem. I mean, it's saying that any non-pathological function that doesn't blow up and all that can be decomposed in terms of a Fourier series, right? Is that clear? I mean, so that's really what we're saying here, and as we let this delta x spread out, what happens is if you kind of let it go to infinity with only one wavelength, then you will have a monochromatic, and you will have, is the delta x spreads out, you get a very large peak here. If you let it compress it in this direction, then you need more and more k values to create that function, right? And so that spread in the k space is delta k, right? And so the product delta x and delta k is greater than or equal to half, and this is half occurs for a Gaussian distribution, and those details, and then you can come, and Heisenberg's uncertainty relation is just this multiplied by h bar on both sides, and that is your delta momentum along the x direction. Right? So that's the same. If your location is precise, then the momentum is uncertain. If the location is uncertain, then the momentum can be more precise, and that sort of thing. Okay? And let's look at one extreme of it. Now, instead of trying to say or talk about loosely defined items like location and momentum and all that, we are going to assign to it a mathematical function which captures all these quantities. And right now, in classical mechanics, that the function is really a pair of numbers. What is the x and what is the momentum, right? In classical mechanics. In quantum mechanics, they are related now, right? X and p are not independent because of the uncertainty relation, right? So, and you know that the mathematical object that captures a connection between a series of numbers is a function. It's not a number anymore. It's a function, right? And so mathematically, if we want to describe the electron and respect its wave-particle duality and its uncertainty, then we must describe it by a function and not just a pair of numbers anymore. Right? That's what we're trying to kind of get to at this point. And that function is really the wave function, right? And instead of writing it as f, we are typically writing it as psi. We can start by saying that let's try to write the wave function for a completely free electron, right, which is not in a metal, not seeing any atoms, or not in a semiconductor. It's a completely free electron, and this is used in modeling. For example, if you're doing electron microscopy, scanning electron SEM, then the electron, when it goes through vacuum, kind of behaves like a free electron, right? So, and so that's the we want to write down the wave function, but there are now quite a bit of constraints. For example, whatever functional form I come up with must respect, the uncertainty relation, right? It must ensure that de Broglie relation is satisfied. All these things should be satisfied. So the wave function is not just any function, right? It is constrained by quite a few things now. It must describe the quantum mechanical electron now, right? So one of the very important, one of the very important things about the function, drawing analogy from electromagnetism, just as a simple analogy. In electromagnetism, if you know the electric field, the energy or the intensity is square of the electric field, right? In electromagnetism, right? This is the amplitude, and here is the intensity, right? So this is electromagnetism. In exactly the same way, Max Born, who is one of the discoverers of quantum, architects of quantum mechanics himself, he gave a very important recipe towards the very beginning, that the square of this wave function tells us the probability of finding the electron at any point. It's the probability density. What does that mean? If I want to find the electron between x and x plus dx in a little window here, then this is the probability of finding the electron between x and x plus dx. It's, you take the length and multiply by the amplitude square of the function there, and you get the probability of locating it at that point. Yeah.
So that was just an old assumption he made. He was like, the square is going to be the probability, and then went forth with that?
Actually, not quite. So let me just say that it was motivated by the mathematical form of, where they were trying to explain hydrogen atom and trying to explain the physical, the functional forms of the wave function that it came out of hydrogen atom. You could see that it must satisfy this way. And later on, when we talk about currents, you will see that this must be the situation. Let me just kind of step back a little bit. In electromagnetism, if you know the name Maxwell, what he did was, before him, all the laws were, Faraday's law, Ampere's law, all those things were around. But he realized that if I have energy, if I'm looking at energy in any location in space, and I want to conserve energy, right? All energy is flowing in are equal to energy is flowing out, or if something is generated here. So that's a conservation of energy. From that argument, he came up that there's a missing quantity which is called the displacement current. It was not there before that. It's exactly the same analogy here. So this mod psi square must be the probability to conserve the number of electrons at any point in space. We'll see that. And when we talk about current flow, transport, of electrons in solids, it comes out just to ensure that there's a continuity equation. It comes out from there directly. So we'll see that later. All right, now, so this is Max Born's interpretation, and if you integrate it over all space, the probability of locating at least one electron is 1, because there is one electron, right? So if you integrate it, so this is a typical normalization condition that's used for the wave function. Whatever function we choose to model the electron, it must be normalizable, and it must satisfy this sort of interpretation that the probability density is mod squared and the total is 1. So that's another very important parameter, piece of knowledge that we need to carry with us. Now, together with this interpretation and the uncertainty, you can kind of we can say a lot of things right now. For example, let's try to ask what is the wave function, or what would be an acceptable wave function for an electron that's completely free to move in space, right? In one dimension, let's say, right? So you can take many, and then one can write that it's oscillating. It has a wavelength associated with it, right? And let's say I'm going to now say a state of electron of definite momentum. This is very important quantity now, momentum. Right? And momentum is one of the almost canonical concepts in classical mechanics, right? Mass times velocity. And now we are kind of trying to ask. We've realized that electrons, I had no issue in classical mechanics to write down the momentum is just mass times velocity, right? But now quantum mechanics is telling me there's more to it. It has a wavelength associated somehow, right? And I must write the momentum for an electron. And what we are trying to do is write down the mathematical function that will satisfy all these things. That will give me the momentum. It'll satisfy uncertainty relation. It'll satisfy everything now, right? And we need to create a function like that. And then we will need to create the wave function of an electron which has a definite momentum. That's what we have to write that down now, right? So you can take a few choices. Typically and we are at this point I'm going to just take a few guesses and then come back to a more structured way of looking at it. So you can think, maybe because it's oscillating, there's a wavelength associated with it. I can write it in this way, 2 pi times x over the wavelength, right? That's an acceptable function that's oscillating in space. Cosine function, let's say, or sine function. Any of those. So I know that function is oscillating in space with a certain wavelength, right? And it's a definite momentum. That means it must have a definite wavelength. P is fixed. Therefore, wavelength is fixed. Just one wavelength, right? Is that clear? So that's we're trying to build it up, and I can do a little bit of, this is not speaking to me, as an electron and something that has mass and all that. If you want to make it a little more physical, I can write it in a slightly different way. I can write that the wavelength must follow de Broglie relation, right? So I can write it as h over p, right? And I also know that h over 2 pi is h bar, so I'm going to write it as x over h bar. It's the same deal. It's exactly the same relation, just a functional form being written in a slightly different way, right? And now let's see whether this actually will satisfy this. We'll be able to model an electron which has a definite momentum, and it satisfies all the tenets of quantum mechanics. That is a wave, it has uncertainty relation, and all that. So. To do that, the first thing we know that if momentum is, if delta p, what is delta p for this problem? It has a definite momentum, right? So what's the uncertainty in momentum here?
Is there a reason why there's the extra line at the top of the p's?
Meaning, oh, you mean like this? No, I'm being a little sloppy. Okay, so, okay. Yeah, it's the same. It's the same, yeah.
I was wondering if there's like a notation for a vector or something.
Oh, no. If I write a vector in class, I'll put an arrow on top. Okay, so yeah, thanks for catching this. No, so there's no vectorial thing right now. So what is the uncertainty in the momentum that of a state that has a definite momentum? It's 0, right? That's by definition, obviously. It's 0. Therefore, the delta x must blow up. It should be very large. Right? I shouldn't be able to say where exactly it is, because in real space, essentially all it's saying is that the wave function is going on forever from minus infinity to plus infinity in x, and this amplitude is that. And so now if I want to kind of see whether that works, whether this function satisfies this delta x, you can go and say, well, Max Born has already given me the prescription to find where the particle is. So if I can locate where it is, I can find its delta x. So you take that and you realize that that's actually cosine squared, right? Right? And you can make a plot of that. And then the plot of that looks, well, you take a cosine function and you kind of it looks like that, right? Is you have these lobes. It doesn't go negative anymore, but it goes to 0 at many points, right? And it's kind of has this sort of behavior, right? And so let me just say that this is unacceptable because it's telling you with certainty that you cannot find the electron here. Impossible, right? Cosine square is 0 at those points, so you cannot find it, right? And that is violating already that delta x is infinity, because it's saying you with certainty that there are some places where you cannot find it, right? And that's not acceptable, so we kind of reject that. That's not acceptable to represent an electron with a finite or with a definite momentum. But with a little tweak here, you can find it, and I think this is how really it came along anyway. So instead of cosine, what if you choose, well, before we go to that, you can see what we need here. What we need is that the probability, when you square that function, that pretty much should be constant. It should be independent of x, right? It should be a constant that's independent of x, right? And that's a very weird function because you need it to oscillate. When you take the function itself, it should oscillate. But the moment you square it, it should become constant, right? And that's a very weird function, right? And there's only one function that does that, and that's the complex exponential, right? So you then see, because if I choose e to the power I, px over h bar, now it has an imaginary part, sure. But if I plot the real part or imaginary part, they are definitely oscillating with x. But if I take mod psi squared, you can see that it's, it goes, it becomes flat, right? So it really is the function that this function can represent, is the wave function of a particle of electrons with definite momentum. It can work in that way. And does that make sense? Which kind of the argument at least that the complex exponential or complex, the functional form, the requirement that it's a complex if it's has a definite momentum, it's unbounded in some sense, and then you are forced to kind of accept the fact that this function should be complex. But every observable, every be its energy, be its location, all those things are real numbers. We're going to get it from here. Okay, so yeah.
Just the normalization constant would have to go to 0, though.
Yes. So if I a free particle in infinitely long space is the wave function is unnormal. You cannot normalize it. I'll show now that physically you can put a bound around it, a certain L, and it's and then when we put a bound around it, you get a normalization constant is 1 over square root of L, and that goes smoothly to, it's essentially as the L size increases, it kind of smoothly goes down. So this is a mathematical construct, as you can imagine, the infinite cases. Right? Physically, you are either inside an electron, a solid, or the whole universe. It has a finite length, right? Maybe. So it's still normalizable in that sense. Okay. So this is a function that can therefore represent a state of definite momentum. But now if you turn the question around and say, if I have a state of definite momentum, or rather, if this is my function, I've somehow measured the wave function somehow, and can you tell me what is its momentum, right? And that you get by what we are going to now say is the space was x and momentum was px, but px is not a number. In quantum mechanics now, the momentum, in fact, every observable will be represented by what we are going to call as an operator, right? And what does that mean? It's going to basically, if I take this object, momentum operator, and it acts on the wave function, it's going to give me, this is the momentum operator acting on the wave function here, will give me the value of the momentum. It will pull out the momentum from the wave function and throw it in front, as long as this state is a state of definite momentum. So that's the meaning of the operator. It will operate on the wave function of the quantum state, and it basically extract from it the value of that physical quantity for you, which this is the operator. So for example, in momentum, operator happens to be minus IH bar, derivative with d by dx. That's the momentum operator. You can see why it should be its h bar, and there's a length here, and the length is kind of the wavelength. h bar by wavelength is momentum, so we kind of construct it in that way. And that acting on a e to the power I px over h bar, right? So you're going to take a derivative d by dx of the complex exponential. So you essentially, it pulls out everything, you know, in front of the x here, and you get I p over h bar times. Again, this is kind of a recap portion of it. But so you can see your minus I and I give you 1, h bar go away, and you end up with momentum times the function itself, right? Yes. So what does it mean? Whatever is sitting here must be the momentum of the particle. That's and this is a function that is a state of definite momentum. That's all it's saying. Now let's say I create a slightly different function situation for an electron that has, for whatever reason, there are two components. It's a little more localized, or maybe you know, it's something like that, and it has a beat of 2 wavelengths. It has 2 wavelengths, let's say. And it can be, it's a superposition state, it can very well be, in which case I will have a wave function that will be, instead of a pure state like that, a pure momentum state like that, it will have A1. Instead of writing P over H bar, I'm going to write it as K now. I think that's K is 2 pi by the wavelength, same thing. We kind of got back to this. So I'll write it as K1 plus A2 e to the power I K2x. Here's a state that is definitely not a state of definite momentum. It's state of, there's some uncertainty in the momentum. It could be K1, it could be K2. So there's certain different, there's an uncertainty there, right? So if I take that and I feed it into the momentum operator, if this momentum operator acts on this, it will not give you, a number in front and the same function. You cannot get it. It's not an eigenvalue anymore, right? So that's a very important thing. So if the momentum operator acts on a state and it gives you a number multiplied by that state is a state of definite momentum. If it gives you a number times some other function and another number times some other function, then it's not a state of definite momentum. That's the physical meaning of it, right? So the momentum operator, and just like the momentum operator, we also have a, if you want to find where's the location of a particle, you can say psi of x, right? So this is the location. Location operator would be just x. And I multiply, if I have a state of definite location, so if I have a state of definite location, meaning in x space, I go in and the particle is somehow here at x naught, then what is its wave function? You can go back and apply the same principle. Whatever be its wave function, I'm going to apply a location operator, and location operator just happens to be x. This is the, wherever you are. And that must be equal to wherever that, value of that here times x. So that should be the eigenvalue equation for a state of definite location. Right? Yeah?
Is that related in the treatment of like the Dirac-Cohn potential?
Sorry?
Is that related to like, the treatment of the Dirac-Cohn potential?
They are related mathematically, but Dirac-Cohn potential, we'll talk about it perhaps in the class on Monday or maybe Tuesday or Thursday next week. Here, this is a kind of a free electron. We are not even, there's no atom in the way. We're just looking at but Dirac-Cohn will play a role like that at some point, in the future. Not yet. But so you can ask now what function will do this, right? What wave function psi will do that? That if I take, it also must be a very strange function because I take the function and multiply any x I want with it, right? And it'll give me the value of x naught. Let's say this is 1 meter times the function anywhere. Right? That's a very strange function. And there's only one, and that is the Dirac delta function. It's not a Dirac-Cohn, but it's the Dirac delta function, right? So if you, so that's essentially saying that your psi here for a particle of infinitely precise location must follow something like that. And if you haven't dealt with Dirac deltas, no worries, we'll deal with it later on. But that's a physical meaning. A state of definite location has a wave function, which is the Dirac delta function. Okay. Now, and location and momentum are obviously extremely important, and they kind of are the hallmarks of classical mechanics, and we know that in classical mechanics we can know both with infinite precision. And in quantum, we have let go of that infinite precision problem, and that's why we have ended up with this wave function that depends on x and p, right? And you can now take these two functions, x and momentum of x, px, which we wrote here, minus IH bar d by dx. That's yes. And you can kind of see that there's a very interesting dynamics. You take any function on the right side, a combination of operators, physical. So what you are saying here is I'm measuring the momentum with the momentum operator of a state, and then I'm measuring where it is. Right? If I first go and measure the momentum of the function, so when this operator acts on the function, it's going to give you the momentum. Then I measure the location. I will get something. Okay? I mean, I get some value from this sort of a measurement technique. But very interestingly, if I first measure the location and then the momentum, in quantum mechanics, you will not get the same thing. And then this is one of the very interesting differences from classical mechanics. In classical mechanics, if the car is moving along a road, you can measure these two with infinite precision. You measure one, the other doesn't interfere. So that's the kind of the meaning. But for electrons, as you might imagine, how would you ever measure the momentum of an electron? You got to hit it with something, a photon or something like that. And that, unlike a photon hitting a car, a photon hitting an electron is a very traumatic event, right? For the electron, it kind of really gets scattered, and you really change its location. You change everything, the moment you do that, right? So that's kind of buried inside this sort of a formalism that if I take x and px, there's a question?
So that's just saying that those operators don't commute?
Yeah, that's right. So what we are saying now is these are not numbers anymore, or operators. So if I take it in this order, you can see now it will give you x, and let me write it down, minus IH bar. The x is outside of f, right? Any function, be it the wave function or any other function. And here you will get minus IH bar d by dx of, now there's a x times the function, right? And now you can apply your chain rule. You take a derivative of this first, and then that next. And you get minus IH bar H bar F, right? And you can take the difference, this minus this. Classical mechanics, that's always 0. But if I take the difference here, you can see that, sorry, there's an x here, right? These two go away. And what you end up with here is that if I did a measurement in this order, and if I do it in the other order, acting on any function. In fact, it has nothing to do with quantum itself. If I take any such two functions, what I end up getting is minus IH bar times that function. From here. So you get this minus this, and this becomes plus. And so here you can see that this function is kind of superfluous here. It just happens to be the wave function for us, but the operators follow this relationship now, that momentum and x coordinates. If I go into the operator formalism, I first measure distance and location and then momentum, and I do the reverse. The answers I get, or the measurement values I get, will be different by IH bar. And remember, H bar is what really defines quantum. If H bar, you take it to 0, you recover classical mechanics. So that's what kind of holds everything together. The fact that they don't commute. Doing one and then the other is not the same as we do it the other way around. I mean, so they're not commuting variables anymore. Right? Okay, so that's about space and momentum. The most important thing we'll be interested in this course will be the energy. So as you know, there's location, there's momentum, and then there's energy, right? And energy is the key for most of the things, and we'll actually next ask the question. We ask the question, what is the state of definite momentum? The state of definite location. And we realize there's a very interesting relationship between momentum and location. Now we're going to ask the question, what's the state of definite energy? And that's where we kind of realize that for momentum and location for quantum objects, you can get away somewhat easy, but for energy you cannot, because energy in classical mechanics, right, is, let's write it this way. Energy in classical mechanics is kinetic energy for the electron plus the potential energy of the electron. If we're looking at one dimension, it's x, and that's your energy, right? But now we just found, because of all our deliberations here, that I cannot have this and the momentum and the location. I cannot know both of them at the same time. Right? It's not possible. So I cannot use this relation, which is a classical mechanics result. I cannot use it, right? And you can anticipate it, that the whole reason. I mean, we know now that the energy and the momentum and x are correlated through the wave function. So somehow the wave function must be playing a role in here, right? And so so Heisenberg had, with Max Born, who gave this interpretation, had come up with a version of finding the energy using matrices. It was called matrix mechanics. And what all these groups at that time were trying to do was they were trying to explain the very precise. If you look at the energy, when you or the energy is if you take a hydrogen atom and you shine light on it and see what comes out, you see very, very discrete and sharp lines, very sharp lines. And those energies were exactly equal to minus 13.6 over n squared in electron volt units, where n is 1, 2, 3, these are integers, quantized. This was experimental observation, which everybody trying to explain quantum mechanics in 1920s and 30s was trying to explain. This was the open problem. This was experimentally verified in many labs around the world, but nobody had an explanation for it, a satisfying explanation. Niels Bohr had a very nice explanation, which was not, which was somewhat empirical, meaning they said that the model electrons as doing orbits, like the solar system, the electron is doing orbits around the nucleus, and he could explain that. But there was no kind of basis that was given to it by Heisenberg and Schrodinger and others. So what Heisenberg realized that to explain this discrete values of energies, we kind of briefly mentioned this in the last class, that this instead of continuous functions typically may not have discrete eigenvalues. Some of them do, but not all. But if you are taking matrices, they do have discrete eigenvalues, right? Matrices. So that's why his proposal, Heisenberg's idea, was X and P are matrices, and therefore this is actually a matrix sort of equation. It's not like a scalar equation that you deal with just it's a matrix equation. And from there he was able to get an idea, basically explain why they should be discrete like that. But Schrodinger came along and he gave, instead of a matrix version, he gave a differential equation version of it. And that's why his name is a bit more popular as far as solving this problem goes. And this differential equation gave solutions of the eigenvalues that are exactly equal to what was measured at that time. And so he explained that for the first time. And that differential equation is really very close to this equation. It's not much different. And what you do here is we have let go of the idea that x or px, for example, momentum is not a number anymore. It's an operator. So we said, all right, I'm going to write it as an operator. Right? And x, in Lie space, I leave it like that. And then I write here, here's my wave function. Okay? And then on the right side, I have a wave function. Okay. So you solve this equation, and this operator is your energy operator. And people knew this a long time before, that this combination, this is called the Hamiltonian, right? I mean, this is from Hamilton, who was a physicist who gave another interpretation of classical mechanics. So it's kind of interesting that his name was used for quantum as well. So this is the Hamiltonian, which is saying that essentially you take your classical energy and make all those x's and p's as operators, just change them to operators. That's your Hamiltonian. And that Hamiltonian is going to act on the function, the state of the function, and only for those states which are eigenvalues of energy, just like you had eigenvalue of momentum. If this state is an eigenvalue of the energy, that energy will appear here as a number. It's a number. That's the eigenvalue problem, and this is the Schrodinger equation. So he's just giving a prescription of how would you find the energies, allowed energies for an electron in any situation if the electron is in a potential V of x. Any potential, quantum well, hydrogen atom, completely free electron, electron, moving close to, or the nucleus, wherever it is. If you know the potential, solve this equation, you'll get the energies. That's his prescription, and there is really no derivation of this. There's only what is called this is one of the fundamental postulates of quantum mechanics. I can give you some explanation how do you derive it, but it's a postulate. There's no way to explain it, no way to derive it. The only proof that this is correct is in experiments. You measure, you calculate it for hydrogen atom, people found it's correct. Calculate for helium, calculate for silicon, calculate for chemicals and molecules. It has passed with flying colors all the things that we have thrown at it till today, so it works, and we believe that this is correct, right? Now, there's some other things. I mean, it doesn't explain spin, and so Dirac came and he took it from here to a slightly more interesting form, which is called the Dirac equation and all. We'll not encounter it right now. We'll encounter it. If we want to talk about graphene and other things in the future, we might have to handle that a little bit in the future, right? But this is enough for understanding most semiconductors. And okay, so again, I'm just giving you kind of almost snapshots here, but this is the prescription. You solve it. For example, if I solve it for the hydrogen atom, I have a proton and an electron going around the hydrogen atom. The potential for the hydrogen atom happens to be minus E squared over 4 pi epsilon naught times R. If your distance of the electron from the nucleus is R, then it's an attractive potential, and this is the potential, right? Coulomb potential. This is the attraction. And you plop that in here, and you solve for it, and you will find that your eigenfunctions look like, s orbitals or p orbitals and all that in 3D space, and your eigenvalues are exactly this, right? So and when people measure these values, so this is, for example, this is minus 13.6, 1 over 1, minus 1 over 4, 1 over 2 square and all that. So those are the all these lines, spectral lines, and it explained them very precisely. So okay, I'm not getting into detail. That's done in most quantum mechanics books. If you want, yeah, there's a question.
Yeah. So you said this equation is for states of definite energy.
Yes.
So what do you mean by what will be states which do not have definite energy?
Yeah, good point. So and we're going to talk about that now. And what do I mean by a state of definite energy? For momentum, it was clear, right? So. Here's an example, but I'm going to be mathematically a little more precise. So you can have a hydrogen atom, and it is actually, so let's say you have two states, E1 and E2, right? The minus 13.6 and minus 13.6 by 4. So there's two states, and there are two energy states here. I can create a situation where I kind of have a continuous stream of photons coming in, right? And that have exactly this energy here. Right? I can create a situation like that. So the electrons were sitting here, but then I came in with electrons, so it goes here. But then I kind of modulate it, right? And then now the electrons could be here or there. It can kind of start going back and forth between the two states. It's very possible to create it. This is a superposition state. And this particular state is the quantum bit or the qubit state people are using for quantum computation today, the superposition of two states, right? So, but you can create, just like you can create a situation of indefinite momentum, you can create a state of indefinite energy as well, and then these are always superposition states.
So by indefinite you mean like
the coefficient.
Time, for a given time they might be in one this.
That's right, and it may go back and forth between them and so on. So we are going to actually look at that in more detail now. Okay, so let's say why, and I'm going to kind of say this, say it in this way, that the states of definite energy are extremely special and they're very, very important for this course. So, and the reason for that is the following. Okay, so this Schrodinger's equation gives us the states of definite energy, but you can kind of realize that I have not finished the task I started out with. The task I started out with is find me a replacement for Newton's laws of motion, right? For electrons, for quantum particles. And this is only giving me energies. It's not telling me how things change in time. This is what is called the time-independent Schrodinger equation. It's time-independent, right? So to finish the story, to find the analog of Newton's laws, Schrodinger also gave us the time-dependent version of the evolution of a quantum state, and it's kind of borrows from there. But here's kind of a time-dependent Schrodinger equation, and this will be kind of the as far we would need to know in quantum. And we'll, when I use it, I'll kind of recap it again. So time-dependent Schrodinger equation is the following. So it borrows from Maxwell's equations, so it's a wave equation. Maxwell's equation is the wave for electromagnetic light waves. This is the solution for anything that has mass. So like electrons or particles. So this is the time-dependent equation for things that also have mass. So I'm going to just write it as a big psi here because it has both. You know what? Let me not confuse you. So I'll write it as x comma t. It's time dependent. That's clear, right? There's both x and time. Right? And the equation that governs is here's an operator that's acting on the wave function that now depends both on x and on time, and that is equal to your time independent part that we wrote on the right side. X comma t. So that's really your final version of the time-dependent Schrodinger equation. In other words, it's this kind of a strange time-dependent operator. When it acts on the psi, it will give me. This is the same Hamiltonian as here. The same Hamiltonian operator. Kinetic plus potential energy. So that's your time-dependent Schrodinger equation. It basically is telling you how is the wave function going to evolve with time, right? And once you know the wave function, applying everything you know now, you can find out. Let's say you subject it to a certain potential. That potential goes into the Hamiltonian here. Go in, solve your time-dependent Schrodinger equation, right? And find the psi. If you know what it is now, find it at some point later, right? Because this is going to govern the dynamics of this function, and then. If you want to find now, well, where is the particle after 50 nanoseconds? Go find mod psi squared after 50 nanoseconds. Go find where it is, right? What is its momentum after 50 nanoseconds? Apply the momentum operator on that psi and get it, right? So it's essentially, it does at least qualitatively, what it's giving you is a prescription that just solve this equation, find the psi for any given potential that the particle is moving in, and you will know all its things in the future, right? Because once you know psi, you can extract from it everything. Does that make sense? Qualitatively, at least, that's the understanding. And quantitatively, what we'll see is, except for like 2 or 3 different potentials, this sort of an equation will be unsolvable. Meaning you have to make approximations, and that's where all this perturbation theory kind of comes in and all that. But at least this is what governs the dynamics. This is the equivalent of Newton's law in quantum mechanics, right? So it's time-dependent Schrodinger equation. So. And what I mentioned a little earlier is that these states of definite energy are very special states in a certain sense, and that will become clear if we look at this time-dependent Schrodinger equation a little more deeper. We're going to apply a few things here and then see that why is states of definite energy important? Why are they? I mean, anybody knows the answer. What's so special about states of definite energy? Sorry? Yeah.
That's what you measure.
Yeah, you can measure them, and when you measure, it will typically collapse into one state and such things. But they have another property which is related to the fact you can measure them. But yeah.
It stays in that state. It's a station.
Right. So exactly, and that's kind of related to what Ryan you were saying too. So states of definite energy are what are also called stationary states. They don't change in time. So if you put an electron in a certain state, unless you do something else to it, it will stay in that state forever. So this is called a stationary state. And you can imagine that, with all these complexities, it is very important to have something that doesn't change in time, because then those are your coordinates. Later on, when we talk about eigenvalues, band structure, we are always going to search for the states of definite energy because they are stationary states. They don't change in time. Everything else is going to change in time, but except the states of definite energy. And that we'll see right now why. From the time-dependent Schrodinger equation. Okay. Let's What we're going to do is, so this is a set of equations that models the electron or protons, neutrons, whichever quantum particle you want to think about. But we're going to, let's say, focus on the electron, and we're going to search for solutions that have one particular nature. Now, this was came up. I mean, Schrodinger came to it. You know, we're going to go in a reverse direction. We're going to say, let's look at a subset of these functions of the wave function of space and time that are what you call as separable, where I can pull out the time from the space. Let's say I look at it like that. So this is why I was trying to probably initially write it as a bigger psi or something like that, because so I'm going to basically separate space and time. So today's lecture is probably the most abstract it will be in the whole course. So if you have questions, I'm pretty sure you must have questions, please come to the office hours and we can discuss. If you, all this is, you know, straightforward and easy, I've seen it before, that's great. You know? But let me just kind of highlight why we are so interested in states of definite energy. They're going to be very, very important. I'm emphasizing it multiple times. Okay? So a state of definite, if I search for no reason really, I'm searching for some subset of the wave functions that satisfy, let's say, my time-dependent Schrodinger equation, that in which I can separate the time variable from the space variable, write it in. For example, if I have a function like cosine kx minus omega t, does that work here? No, it doesn't. Right? You cannot separate it. X and t are not separable here, right? So that's not a kind of function I'm looking for at this point, right? Does that make sense? But if I'm looking at e to the power I kx minus omega t, does that qualify? Yes, because this is written as I kx times e to the power minus I omega t, and that is indeed separable. Okay. So that's the class of functions I'm looking at right now. Now cosine, you can try it, it won't work. You know, even if you go into Euler relation and all that, it won't work. Right? So you're forced to do complex numbers again. But for this subset of functions, potential candidates for wave functions that satisfy the time-dependent Schrodinger equation, you can take this and plop it in here. And on the left side, what I get is IH bar, you know, time derivative. But the time derivative only acts on this thing, not on that, right? And it takes you, gives you the time derivative, which is chi. I'm going to put a dot on it. That's the time derivative, right? And it leaves my psi alone, doesn't mess with that. And on the right side, I have the Hamiltonian. Now, Hamiltonian has no time in it. Only space d by dx's and space, right, potential in space. So the Hamiltonian only acts on psi and it'll do something to it, but it leaves the chi alone, the time alone. It doesn't do anything to it, right? So you can pull out the chi here, and you pull out kind of the psi stays separate. Does that make sense? I mean, that's essentially separation of variables. And then you take the chi here, and you take the psi here. These are well-behaved functions. You just take them here, and you get a very interesting looking equation now that's saying that for those subset of functions which are separable, time and space are separable, you have basically, you know, the chi and the h, chi and psi should satisfy this relationship for that subset of functions. But you look at it and realize this is actually very interesting, because on the left side, this is a variable of time, it's changing with time, right? On the right side, has no time at all. It's all variable in space, or x, right? It's a variable of x, variable of time. So I can sit at one point of time and I can scan through all x's. I can be changing this function, right? Does that make sense? Then I can't be equal to the left side unless there's only one situation when I can satisfy this for all times and for all space, right? And that's if both of these are a constant, one constant. Does that make sense? There's only one situation where it will work, and that's when this thing is a constant. And I think looking at this, you know what dimensionally what should that constant be, right? It's h psi. Hamiltonian acting on psi is going to give you the energy, and that's the constant, the energy of the quantum state. So this is basically the upshot of this. So argument, again, recounting the argument, you get here's Schrodinger's time-dependent Schrodinger equation. Every quantum state must satisfy, the wave function must satisfy this relationship. Now I'm going to look at a subset of those wave functions in which I can separate the time and space variables. The moment I look at that, I realize that this quantity and this quantity must be equal, and that's a constant. And from here, I realize that constant must be from the time-independent version, right? And that's the energy. And therefore, those functions that satisfy this relation, I'm going to label it with a sub E. These are the eigenvalues allowed for the electron. This is the states of definite energy, psi E. These are the states of definite energy. And why stop there? You can actually solve this equation and find your chi exactly, right? From here, right? You can find, you take your chi, which is a function of time, right? So I think you can, I'm going to just write it down here, chi of t, because this, you got a d over dt here. That's just E, and then chi at 0 times e to the power minus I energy over h bar t. So that's the function. You can see if I take the time derivative, you get e I over h bar, and that I h bar cancels, you get just energy, right? So this is how the time component of these states of definite energy evolve. And then we basically, from here, I can write down the total wave function for any situation which has a state of definite energy. Right. So I'm going to basically use the subscript E for all those states that have definite energy, and I found that chi must be, so it must look like e to the power minus I energy over h bar t times a spatially dependent solution that you get from the time-independent Schrodinger equation. So now again, now you can find out how does it evolve in time. So you go and if particle was here at this point of time, where will it be at 10 nanoseconds later or at a future point of time? Then I think you can to find that, you go back to Max Born and say, well, I want to find mod psi squared. That's going to tell me where is the particle now, right? And take mod psi squared at any time, you realize that the mod square of e to the power minus this thing is just 1, right? It's called a unitary evolution. So it doesn't change in time because the mod square of this is not oscillating in time, and that just happens to be at whatever it was at time t is equal to 0. It doesn't change. Right? So that's the stationary behavior of the quantum state because the time variation is a complex exponential. Yeah.
So when we were doing the states of definite momentum, we had to stipulate the requirement that the potential is either 0 or perfectly very large. There's no spatial variation in the potential, right?
Are you talking about states of definite momentum?
Yes. So here,
no. So state of definite momentum, we did not talk about potential at all.
Right. Well, so the potential is totally 0. Okay.
That's right.
But here, when we have the time-dependent Schrodinger equation, we are assuming the potential is perfectly constant in time.
Very important point. That's right. At this point, we are assuming that v of x is just v of x. There's no time.
Right, so we can,
very important. Yeah.
We can only obtain the states of definite energy with that stipulation.
Yes.
And I'm wondering, in matter, where we clearly have, let's say, an electron whizzing around, and there's a bunch of other electrons that are also whizzing around, it's not going to experience potential that's
absolutely
time.
Right.
So I'm wondering how realistic the state of definite energy is in.
Right. So the way it's built upon is you first say that, for example, a great example is the atoms. Are they sitting still or are they vibrating? They're already vibrating. So v of x is actually changing because of the atom too, right? But the way you deal with it is you say they're going to sit at wherever they are. But then on top of it, I'm going to add a time-dependent perturbation to it. And that's why we are looking at the state of definite energy, because all the changes we're going to look at are very small perturbations around that. And meaning here we're looking at 13.6 eV sort of energy scale or 5 eV energy scale, and most perturbations like a phonon would be 10 millielectron volts. So that's why we deal with it, and we'll see when it comes why we say that the state of definite energy, we make a lot of approximations and take the best case scenario that nothing is moving, nothing is changing with time, find the eigenvalues, and then let it evolve around those energies. So yeah.
If we're only looking at the ground state systems, do we have to include that perturbation in time?
For a ground state, that's a good point. So in a ground state, you don't have the time-dependent perturbation either. Meaning, if you are at 0 Kelvin, for example, right, you won't have these perturbations either. So yeah, that's right. So we'll discuss this in the future. But here's the reason, though. Why are we doing it this way? We are saying that the potential is not changing in time, and then later on we'll let it change. The phonons or photons, all of them will have a time-dependent oscillating potential. Okay, so that's an important relation for particles that, you know, with time evolution, that if it's in the state of definite energy under this criteria that your potential is not changing in time, right? Then the state of definite energy implies that the wave function is staying put; it's not changing. Right? And that also is kind of the analog of Newton's first law of motion, which says that if your particle of constant velocity or rest is going to continue moving in that unless you apply a force on it, right? First law, Newton's first law. This is the first law of quantum mechanics, that if you have a state of definite energy, it will stay in that state indefinitely till you perturb it with some other thing, you know, hit it with light or do something like that. That's analog to that, yeah. Yeah.
So the separation of time and space,
right,
on the wave function.
Yes.
Is that the assumption to make all the time when you are looking at states of definite energy? Because it looks like it falls out that at the very end you remove the time from the squaring.
Uh-huh.
So can you just always say whenever you have a state of definite energy, it's always going to be separable, or no?
Oh, I see. You're saying whether the reverse is correct. Yes. So in a certain basis set, it will always be separable if you have a state of definite energy. Yes. Yeah. Now what we're going to do is, so most of the first part of the course we'll be talking about time-independent Schrodinger equation. We'll apply it to electrons moving in silicon, in metals. We are going to resolve the problems with Drude model, specific heat, all that stuff. And all that stuff will come out from here. And then maybe a month into the course, we'll start looking at the time-dependent version. And we'll apply it to understand transport phenomena, where electrons are moving through silicon or metals. And then how light interacts with the electrons in semiconductors. How do you create LEDs or lasers? I mean, the idea of that, those are all time-dependent phenomena. So we're going to kind of go back and forth between the two. In the course. But before we go there, for the last few minutes today, what I wanted to do was just finish up with an argument. I did not kind of yet get to that. So that's your time-dependent Schrodinger equation. What we're going to now say is instead of one particle, one electron, I'm going to ask the question, what if I had two electrons, right? Just go from 1 to 2 electrons. And ask very simple questions first, like what is the wave function in a situation where I have, here's my space, and I have, x1 and x2 are 2 points in space. And you can imagine that this is maybe a nanotube or something like that. And here's an atom. If an electron is sitting here, maybe it has like a s orbital state. I mean, like it's spherically symmetric. Maybe. I mean, this is as an example. It doesn't matter what physical situation we're talking about. Maybe if it's here, it's in a p orbital like state. So its wave function squared looks something like that. The shape of the wave function is looking something like that. If it is here, is one atom which can hold an electron in an s orbital, another atom which can hold it in a p orbital, as an example. So this state, I'm going to call it a state A, and it has a wave function psi of A. That state, I'm going to call it B, with a wave function psi of B. Is it clear what we're doing? We are now going into 2 electron situation, a multi-electron situation. Everything we've done till now is 1 electron, going to 2. And this is where a lot of interesting things immediately kick in, because you can ask, if I put 2 electrons into this, basically I'm going to have 2 electrons. I'm going to put them in these 2 orbitals. What is the wave function of this combined situation, right? When I have both the electrons, right? So what is the wave function x1, comma x2? So it must take into account both the electrons, right? So what will be the wave function here, right? And I know the time-independent Schrodinger equation solutions for both of them separately. I know that. So what would it be, right? And will it be, what functional form will it take? So, will it be a sum, product, difference? Yeah.
Isn't it usually a linear combination?
Will it be a linear combination? So let's see. So if I write it as psi. Remember, the question we are talking about is not 1 electron, but 2, right? There are 2 electrons here. And so if I write it as psi A plus psi B, you can see you kind of run a bit of problem into energy, because this state has, let's say, energy EA, this state has energy EB, and if you go back and look at this sort of how does energy play a role, you see it controls the energy here. The total energy would be EA plus EB, right? And the wave function then tells you that you must take, it must be sitting in the exponent, it must be summed in the exponent, right? Therefore, the functions should be a product for 2 particles, right? For when you're doing 1 particle and you're linearly superposing 2 possible states, then you take a sum or a difference. But this is a 2 particle situation, it's very different, and this must be a product. So that's a very important parameter and a thing to realize, that the moment you go into multi-particles, you multiply the wave functions, because the energies are adding and the energy is sitting in the exponent, right? So, right. Okay, so, and I think I'm almost done with time here, but you can see now that it can look something like this, psi orbital A, and location is x1, because you must also define 2 variables for where are the 2 particles. There are 2 particles, x1 and x2, right? So this is a possible situation, and this is actually acceptable as long as these 2 particles are what you call as indistinguishable. If you cannot distinguish the 2 if they are distinguishable. If this is an electron and this is a proton or a neutron, then this is acceptable. You can accept this. But the moment they are indistinguishable, like both are electrons, let's say, this is not an acceptable function. Right? And the reason for that is very important. I'll kind of repeat it also on Thursday, but let me just finish up the discussion at this point, because the Born interpretation says that x1 comma x2, if I take a mod square of it, that's the probability of finding both particles in these 2 orbitals, one in here, one in here, and then I get psi A of x1 squared and psi B of x2 squared. So this is a product of 2 functions. One may be a sine function, or the other may be a cosine or whatever. Right? So different functions. But now, because they're indistinguishable, I'm free to swap the 2. Right? I can move this over here, and the probability must not change, right? Because they're indistinguishable. Right? But you see now, if I try to swap the 2 variables here, I get psi A of x2 squared and psi B of x1 squared. Now, is this function form same as this? No, it's not. It takes a completely different number. It gives you a completely different number, right? So it's not allowed. And this wave function is not allowed. The product in this way is not allowed for indistinguishable particles. It's a very important result, right? And then you ask, is that clear? I mean, like sine of 2 and cosine of 3, and cosine of 2 and sine of 3 are not the same. So it's not allowed. Right? So what is allowed? And you can kind of hook up now. You can look at this and say, well, here's what I'm going to do. I'm going to take this plus, I'm going to flip the things around on the right side here. I'm going to write it psi A of x2 and psi B of x1. I'm going to just flip the 2 around. This is another try. Right? Is this allowed? And you see this is indeed allowed, because now you swap x1 and x2, this turns into that and that turns into this, and the number stays the same. Right? So this is called a symmetrized wave function. This is allowed, and in fact, there's another one that's allowed, x1 psi B of x2 minus psi A of x2 and psi B of x1. That's also allowed. Why? Because when you flip the 2, you'll see you get a negative sign in the front. But Born interpretation is going to take mod square, and that still stays the same, negative sign in the front, right? Now, this is just an incredible, to me, it's just one of the most beautiful things in quantum mechanics, that the moment you realize this, you realize that every indistinguishable particle in nature, if I have 2 electrons, 2 protons, 2 neutrons, 2 photons, whatever be it, they have to make a choice. They either go with a plus sign or a minus sign. Right? There's no other option. With the asterisks, I'll talk about that things later. There are some things called anions now, which is recent. They must either make a choice of plus or minus, right? And the ones that choose the plus sign are going to be called bosons, right? These are photons, phonons, all that sort of thing. Bosons, and the ones that choose minus sign will be called fermions. That's electrons, protons, and such things. And Fermions have a very unique property that now if you want to put, let's look at bosons. If I put x1 and x2, both of these particles in the same state, then I get, x1, this also becomes x1, that becomes x1, that becomes x1. No problem, you have some function here, right? If I try to put both particles in the same state now, right? Same state. But if it has chosen the minus sign, you can see that if I try to put both particles in the same state at x1, you get what? This minus this is 0. So the wave function is 0, the wave function squared is 0, right? You cannot put two of those particles that have chosen the negative sign in the same state, right? And that's the fermions follow that, and that's the Pauli exclusion principle, right away from here. Okay, good. So that is the heart of basically this new statistics that emerges, Fermi-Dirac statistics, and we'll start from there, and that's what we're going to apply to explain where this thing comes from, the resolution of the specific heat comes from. But it can be tracked down to this relation, the Pauli exclusion principle. Okay, good. So let's meet next week on Tuesday then.